All right, this is our Module 1 review, end of unit review we're doing together. And so we're going to actually start at number 5. So 1 through 4, don't do. We're going to start at number 5 and we're going to do it together. So this is a rational function. The first step is to factor it. So that's positive 4 and positive 1. Factor out of 3. And then continue to factor it. So it's negative 2 and positive 1. All right, so step 1 is to factor it completely. The domain restrictions come from the denominator. That's positive 2 and negative 1. 3 has no restriction. I'm not going to worry about the range until I look at the graph, and if it's obvious, great. If it's not, I'm not going to worry about it. X-intercept. Well, now we have to look, is there a hole in this function? So negative 1 is removed, or x plus 1. The 0, negative 1 becomes a hole. So what's left over is x plus 4, 3, x minus 2. So I'm going to plug negative 1 in and find the hole at negative 1. So negative 1 plus 4 is 3. Negative 1 subtract 2 is negative 3. That's negative 9. I get negative 1/3. Double check that. So we have a hole at negative 1 and negative 1/3. What remains in the denominator, the restriction, is a vertical asymptote at 2. Notice how the powers are even. They have the same power on the top and bottom. When I divide the power terms, I get 1/3. So be careful of that. It's 1/3. There is no slanted asymptote. Where's the x-intercept? That's what remains on top. The 0 is negative 4. It's odd, so it's going to cross. The y-intercept, if I put in 0 and I solve it, I get negative 4 over 6. So we can write that as negative 2/3. Lots of fractions in this one. And increasing and decreasing, I'll do that after I do the graph itself. Anything else? I think we're good. So let's graph this. So let's start with the asymptotes at 2. And there's another one at 1/3. You can only estimate that one. There's a hole at negative 1 and negative 1/3. There's a y-intercept at negative 2/3. And there's an x-intercept at negative 4. All right. So I got lots of information on the left. So I'm going to connect this, curve it. What's below here, it's going to go to negative infinity, and the left end is going to go here to the asymptote. On the other side, I'm going to find a point to plug in on the right and then plug it in here. So I'm going to plug in 3, see what answer I get. So if I plug in positive 3, I get 7 in the numerator, and then 3 take away 2 is 1, that's 3. So that's just a little bit more than 2. So I'm going to go to 3 and a little more than 2, 2 and 1/3. And now I have a point to curve through. So it's going to go to infinity and then curve, and then that's the end behavior. So where is it increasing and decreasing? So this, if I look left to right, decreasing means it's falling. So this is decreasing from negative infinity all the way to the vertical asymptote, which is at 2. So it's decreasing there. This is also decreasing from 2 to infinity. So it's decreasing everywhere. Technically, 2 is not either one because it's an asymptote, and it never increases. All right, number 6. Let's do this graphing together. So number 6, the step 1 is to factor. You should always press pause and try to do it before I do it, then press play. So the numerator, it's negative 4 and 1. The denominator, factor out an x. No whole. If I look at the powers, they're the same. So anyways, the denominator, x cannot equal 0 or negative 3. They're both vertical asymptotes at 0 and negative 3. There is no whole. I said that already. Horizontal, x squared and x squared. So they're even powers, equal powers. Divide them and you get 1. So let's put that on the graph right now. So 0, negative 3, oh, I did that wrong. So 0 and negative 3, that one I did right. Ignore this. The horizontal one is at 1. There we go. Little correction. So 0, negative 3, and 1. By the way, the range here is actually pretty obvious that the y value can't be the y value of the whole, which is negative a third, and the horizontal, which is positive a third. So those are the two numbers y cannot be. Oops. Filling in here. So negative 1/3 is the y coordinate of the whole. The horizontal asymptote is positive a third. Those are the two numbers that the range, those are the two numbers it cannot be. All right. Back to this. Intercepts. So look at the numerator. Positive 4 and negative 1. Both of them are odd. It's going to cross at both of them. The y-intercept, it doesn't exist. If you plug in 0, it's undefined. And there is no slanted asymptote. So let's graph what we have. So 4, 0, negative 1, and the y-intercept at, oh, it doesn't exist. So let's curve this. So here we have, it's going to go to negative infinity and then curve to the end behavior here at the horizontal. This one's tricky. So for this one, this is what's considered an odd vertical asymptote. So if it has an odd exponent, one end goes to negative infinity and the other end goes to positive infinity. And it feels a little complicated because it's crossing the horizontal asymptote. A function can cross the horizontal. The horizontal ultimately gives you the end behavior. A lot of times it does not cross, but sometimes it can cross the horizontal. So our analysis is that it crossed the x-axis. So at this intercept, it crosses over. And at a vertical asymptote, it's either going to go to infinity or negative infinity. So when I look at this function here, I know that it went to negative infinity, and this is what's considered an odd vertical asymptote, which means the degree or the exponent on x or 0 is odd, which means one end goes up and one end goes down. X plus 3 also has an odd exponent. So if this goes to negative infinity, on this side it goes to positive infinity. So if there's an odd exponent on a vertical asymptote, they go in opposite directions. If it actually was an even exponent on a vertical asymptote, they go in the same direction. So I need a point still to curve through here. I'll do that. I'll plug in, what do we have here? Negative 3, so negative 4, negative 5, and then we have a point to curve through. So negative 5 and negative 4, negative 5 plus 1, negative 5 plus 3, and then see if I can simplify this down and put it on my graph. So this becomes 2, and a negative is positive. So this is like 3 3/5. So like 3.5. So negative 5. 1, 2, 3 and a bit. There it is. So now I have something to curve through, and that's it. There's the graph of the function. A little bit challenging, right? But we did it together. Notice how it goes up forever and down forever. So that means the range is all real numbers. There is no restriction to the range. Number 7. So step 1 is to factor this. So I'm going to factor out a 2x. That's x squared plus 4x minus 5. The denominator, I'm going to factor out a 2x. That's x plus 1. Now, in the numerator, get my face out of there, the two numbers that multiply to negative 5 and add to 4 are positive 5 and negative 1. So before I reduce it down, there's a 2x gives me the restriction of 0. X plus 1 gives me the restriction of negative 1. Notice that the 2x eliminates. So we have a hole at 0. So of what's left over, plug in 0 for the y value. So if you plug in 0, you get 5 times negative 1. So it's negative 5 over 1, or negative 5. So we have a hole at 0 and negative 5. We have a vertical asymptote at negative 1. The degree on top is bigger than the one on the bottom. Now, I can still use synthetic division here to find the oblique asymptote because it's one, the power is one bigger on top. I'm trying to find like the best angle here. I'm going to get it. I'm going to get it. No. All right. So if I use synthetic division, x plus 1, that's negative 1. If I multiply this out, x times x is 1x squared. And if I FOIL it, I get 5 take away 1, which is 4x. And the last number actually doesn't even matter. So if I do this, I drop the 1. Negative 1 times 1 is negative 1. And the remainder has no consequence on the oblique. So it's x plus 3 is the oblique. The x-intercept from the numerator is negative 5 and 1. They both are odd. They're going to cross at both. The y-intercept does not exist because we have a hole on the y-axis. And there's no horizontal asymptote. So let's graph what we have. So negative 1. We have an oblique at 3. X plus 3, so I start at 3. So there's the oblique. We don't have a y-intercept. Instead, we have a hole at negative 5. We have an x-intercept also at negative 5. And at positive 1. And now I'm just going to complete the curve. So this curve from this point goes to infinity at the vertical and goes to negative infinity following the oblique. Same thing here. It goes to infinity and then it hops over the hole and goes to negative infinity. So you have the two curves. The range, again, this is actually going to go up forever and down forever with no breaks. So this hole, there's a y-coordinate over here that covers for this hole. So in other words, the range is all real numbers here. All the y's are covered because this goes up forever and down forever with no breaks. So even though there's a hole on the right, this curve goes up forever and down forever. Intervals. Did I even do increasing and decreasing the last one? I did not. So this one increases from negative infinity to the asymptote at negative 3. It increases from negative 3 to, what's the other asymptote? 0. And then it increases from 0 to infinity. So it increases, it increases, it increases everywhere, and it never decreases. And we only write it this way because we have asymptotes in between. How about this one? Number 7, left to right, it is increasing and it's increasing. So, and there's only an asymptote here that would break that up. So from negative infinity to negative 1, and from negative 1 to infinity, the function is increasing left to right. And it never decreases. All right, we're on to number 8. These are super challenging, fun questions. Here we go. Can I see everything I want to see? Here we go. All right, step 1 is to factor. Factor out a 3. In the denominator, factor out an x squared. Factor out a negative 9. So we have 3. That's a difference of squares in the numerator. In the denominator, we also have x squared subtract 9. So x squared subtract 9 is a difference of squares. And then we still have an x subtract 6 there. So x subtract 6, what's left over is x squared subtract 9. That's a difference of squares, so I just did that step. Before I do anything else, there are 3 numbers. They can't be positive and negative 3 and positive 6. Then you can eliminate. So positive 3 and negative 3 create holes. So this graph has 2 holes. Is that allowed? Yes. You can have 3 holes, 4 holes, 5 holes, 6 holes, 7 holes, and so on. As long as something eliminates and gets removed from the denominator, it does create a hole. In this case, 2 factors are removed, so we have 2 holes. What's left over is 3 in the numerator and x subtract 6. So something really simple. If I plug in positive 3, I get 3 over negative 3, or negative 1. If I plug in negative 3, negative 3 take away 6 is negative 9. So that's negative a third. So those are where my 2 holes are. What remains in the denominator is a vertical asymptote. If I look, the top is weaker than the bottom. The bottom is more powerful, so the horizontal asymptote is 0, and there's no slanted asymptote. The x-intercept, what's left in the numerator, 3 can never be 0, so there's no x-intercept that exists. If I plug in 0, I get negative a half. So there is a y-intercept at negative a half. So I'm going to put down what I know. So 6, that's the vertical. 0, that's the horizontal. We have a hole at 3, negative 1. We have another hole at negative 3, negative a third. So we have 2 holes here. We have a y-intercept at negative a half. So all of that, the 2 holes in the y-intercept are going to connect. So on this side, connect the y-intercept and the holes, and then follow the curve of a rational. So the left end behavior is the horizontal, and then the right end behavior goes to negative infinity at the vertical asymptote. We do need a point here on the right. So if I plug in 7, 7 take away 6 is 1. So that's 3 as an answer. So find 7 and 3. There it is. So now I have a point to curve through. So this goes up forever here to infinity. And then the right end goes to the horizontal as its end behavior. This function is decreasing all the way through. Left to right, it's going down. And it never increases. It's only going down with a couple holes. All right, let's turn the page. No more graphing. Break your little hearts. So here we go. This is a graph, but we're not graphing it. Given the graph of a polynomial, determine the sign of the leading coefficient and whether the function has an even or odd degree. So in other words, the power term. So what do we know? The ends are going in opposite directions. So that means the power term has to be odd. The right end's going down, so that means it has to be negative. So a power term that's negative with an odd exponent, the right end goes down, the left end goes up. Number 10. Notice both ends are going down. That's even. So the power term is even, but the right end and the left end are going down. So it's an even power term with a negative sign in front. Number 11. First of all, is it odd or even, the exponent for the power term? So because they're going in opposite directions, the right end goes up and left down, so that means it's a positive with an odd exponent. So if you have a sketch of a polynomial, you know the power term and whether it's positive or negative, and if the degree is even or odd. Moving on, number 12. Number 12 says, divide using synthetic or long division. That was a long time ago, right? So this is a simple linear, so I can use positive 6 to divide. We have 2x to the fourth, negative 8x cubed, negative 22, negative 15, and 20. I'm going to add and multiply and move my way across here. So I'm multiplying, then I add, I multiply, and then I add. And then, do I remember how to write the remainder correctly? So when I divide, my answer is going to be 1 degree less than the dividend of what I started with. So in this case, it's going to be 2x cubed plus 4x squared plus 2x, subtract 3, and then the remainder gets written as a fraction, where it's 2 over the divisor. And there's your answer. That's what's called synthetic division. Number 13. Again, a simple linear. Take the 0 of the divisor, which is positive 1, and then we have 5x to the fifth, negative 5x to the fourth, 1x cubed, 0x squared, 4x, and negative 2. So don't forget the missing power. Drop the 5 down, multiply, add, multiply, add, multiply, add, work your way across. And now once you have that, can you write that properly? So the dividend was x to the fifth. So my answer is 5x to the fourth, no x cubed, plus 1x squared, plus 1x, plus 5, plus 3 over the divisor, x minus 1. Number 14. Not a simple linear. I need long division. So write it out. Be aware if there's any missing powers. There's not. Just the power terms, the leading power terms only. So 20 divided by 5 and subtract the exponents. Now multiply. This is where you might make a mistake. When you subtract negative 4, subtract negative, these all eliminate. So what's left is 10x plus 1. So 10x divided by 5x is 2. There's the remainder. When you subtract a negative, you're adding. So we make sure that 3 is written as a fraction in our answer at the end. Number 15. Again, I need long division because it's not a simple linear. So write it out, no missing powers, just power term over power term. So 3x cubed divided by x squared, that's 3x, multiply it, 3x times each term. Subtract to find the remainder. So 20 take away 18 is 2. And 14 take away 3 is 11. 2x squared divided by x squared is 2. Again, multiply by to each term. So you get 12x and 2. Subtract. I have negative 1x and negative 10. And then your final answer is going to be 3x plus 2. And then the remainder, you can write down plus and then put negative x subtract 10 over the divisor, x squared plus 6x plus 1. Done. If you put down subtracting, then both of these would have to be positive. All right. Number 16. Do you remember the rational zero theorem and the remainder theorem? So the remainder theorem is a way to evaluate. If I want to know what is f at 3, instead of plugging in 3 and calculating it out, I can use synthetic division, and the remainder is my answer. So I can go 3, and we have 1, negative 4, 1, and 6. And then I could do the synthetic division, which often is smaller and easier numbers to work with. And in this case, the remainder is 0, so f at 3 equals 0. So actually, x subtract 3 would be a factor. Let me see if I did that. Let's try it again. Number 17. So the remainder theorem is there's a different way to evaluate. So if you want to evaluate at negative 2, the remainder, when you divide, gives you that answer. So that's 4, negative 3, 0x squared, 7, and negative 11. So don't forget the missing power. So it's 4, negative 8, negative 11, 22, negative 44. That's negative 37, 4 and 3, yep. And then 74. So then the 74 take away 11 is 63, and that's your answer. So it's the remainder we use to evaluate. Number 18. Now, plugging in 1 is so simple that I wouldn't even use the remainder theorem, but I'm still going to do it. So using 1, and the remainder is negative 4. So it evaluates to negative 4. Again, this is called the remainder theorem, another way to do substitution or evaluate a function, a polynomial. So negative 3 again, my goal is to know what f at negative 3 is. I'm going to use synthetic division to do it. 2x to the 4th, 5x cubed, 0x squared, 3x, and 4. And I get the remainder to be 22, so that's the answer. So that's called the remainder theorem. Now, attached to the remainder theorem is called the factor theorem, that when you do synthetic division with the 0, if the remainder is 0, it's a factor. So if I want to know whether x plus 1 is a factor, then if you plug negative 1 in, the answer should be 0. So if I use negative 1, what's the remainder is what I'm looking for. A remainder of 0 means it's a factor. So as I do the work, I see the remainder is 0, so this is a factor. So I check mark it. So the next one would be positive 4. If that gives you 0, then it's a factor. So use positive 4 to 2, negative 3, negative 7, negative 12. I get the same answer. I get 0 again. So this one works. The last one, negative 3, it probably doesn't work. We'll see. And it doesn't. And it doesn't even matter what this is. As long as it's not 0, it's not a factor. So that's called the factor theorem. So if you do synthetic substitution and the remainder is 0, then that's a factor. Let's try it again with 21. So let me just do that. So x plus 2, that would be take the 0, which is negative 2. Be careful if there's any missing powers. There's not. So use negative 2 and see if the remainder is 0. That doesn't work. So x plus 2 is not a factor. The next one we try is negative 4. Notice that negative 4 does give you a remainder of 0, so that's a good answer. Last one to try is 6. Once you've done these a million times, which I probably have, then it gets quicker and quicker to do these. That's 300 and, this is going to get ridiculous, 312. So is that going to give me 0? I'm not even going to bother with it. The numbers start to get too big. So that doesn't work. So the only factor was x plus 4. All right, 22. Do you know how to create a list of possible rational zeros? So the leading number is 1. So just all the numbers that go into 42 evenly. That's 1, 2. That's 3. That is not 4, not 5, 6, 7, 14, 21, and 42. I think that's all of them. Number 23. So again, the leading number is 1, so I can just work on P, the last number. What are all the numbers that go into 15? There it is. 24 and 25 are a little more challenging because the leading number, it's different. So I have 24 and 3. So all the numbers that go into 24, which is this, a lot of numbers. So those are all the numbers that go into 24. And then you take all those numbers and still divide by 3. So that's 1/3. That's 2/3. 3 divided by 3 is 1. So it's already there. 4/3. 6 divided by 3 is 2. 8 divided by 3. 12 divided by 3 is 4. And 24 divided by 3 is 8. So that's a complete list. Again, 28. All the numbers that go into 28 evenly. There they are. Now we do have 2 in front, so we have to divide all these by 2. Now 2 divided by 2, that's 1, and 4 divided by 2, that's 1. 4 divided by 2, that's 2, so they're already on the list. 7 over 2, 14 over 2 is 7, and 28 over 2 is 14. So that's a complete list. So do you have the ability to create a list of possible rational zeros? Descartes rule of signs, we're not going to do. So cross 26, 27, 28, and 29. That's right. Cross them out. Here we go. Turn the page. Number 30. So it says find all the zeros and give the complete factorization. And you might have to use the rational zero theorem. Simplify all the irrational and complex solutions. All right, here we go. So for number 30, this is factorable right away. So let's do that. So the two numbers that multiply to 72 and 14, I think are, what is it? 4 and 18. So negative 4 and positive 18. Tough, right? But they do multiply to negative 72 and add to 14. X squared subtract 4 is a difference of squares. Well, x squared plus 18, I have to write by itself. It's not factorable. Make it equal to 0. So the quadratic factor that can't factor any further, make it equal to 0, subtract 18, and then when you take the square root, it's going to be positive or negative. The square root of a negative number is imaginary, and the square root of 18 is what it says. I don't even care if you reduce it down. So it's I root 18, positive and negative. So if I do the complete factorization, it's x plus 2, x minus 2, x minus I root 18, x plus, so it's subtract the negative, x plus I root 18. So that's considered the complete linear factorization. So the zeros would be positive and negative 2 and positive and negative I root 18, and those are it. Now that's called the fundamental theorem of algebra, where the degree tells you how many zeros there are, whether they are real or imaginary. Number 31. Step 1 is to factor it. Now, this is not factorable by, if you factor out a common factor, they won't match. So then what do? Is I create a list. So you have positive and negative 1, 2, 3, 6. There's my list. Now I also need to divide it by 5. So that's 1/5, that's 2/5, that's 3/5, that's 6/5. Ugh. So look at this long list and lots of fractions. I'm going to help you. Positive 1 does not work because it doesn't add up to 0. Negative 1 does work. I'm just going to help you. That's 5, 12, 1, and negative 6. When I do the division, what you're left with is 5x squared plus 7x minus 6. This is factorable. So two numbers that multiply to negative 30 and 7. I think it's 10 and negative 3. So we have 10 and negative 3. Now you can factor by grouping. So the first two, factor out a 5x, factor out a negative 3. Now I can put this all together. So they're all linear factors. So all the linear factors then, negative 1 is x plus 1. We have x plus 2. And we have 5x subtract 3. Those are all linear factors. And that means the zeros, each factor has a 0. So we have negative 1, negative 2, and add 3, divide by 5. And those are the zeros of the function. And the linear factorization. Everything was real in this one. Number 32. So if you try to factor by grouping, it doesn't factor. So we need a list. The first thing I look on the list, that's 15. The first thing I look on the list is if you add them together, does it add up to 0? And actually it does. So 1 take away 3, take away 13, plus 15, that adds up to 0. Positive 1 works. So if it works, take it and divide. What's left over is not factorable. So we have 1x squared minus 2x subtract 15. So no diamond can factor this. So I'm going to add 15 to the other side. I'm going to solve this by completing the square. So it is a simple quadratic with an even linear. Take the negative 2, divide by 2 and square. That gives me negative 1 squared, or 1. I'm going to add 1 to both sides. You know what? It is factorable. Isn't it factorable? Negative 50. You know why I know it's factorable? Because the square root of 16 is not irrational. It's totally factorable. It's 5, negative 5, and 3, right? This is like, what the heck? Let's try that again, right? So negative 5 and 3, and then positive 1 is negative 1. So that's the linear factorization. Negative 5, 3, and negative 1. Perfect. Next, zeros. Positive 5, negative 3, positive 1, all real, all rational, and I just tried to make a headache out of it. That was unnecessary. 33. So for 33, look carefully. If I factor by grouping, it does not factor. So the list is long. All the numbers that go into 36. And I will help you. So the number that goes in is -4. You're welcome. Otherwise, you just keep guessing until you got a remainder of 0. All right, what's left over? This one I know is not factorable. I know it. So I'm going to add 9. You know that -2, like the work I did over here? It belongs here, I guess. So -2 divided by 2 squared. So I'm going to add 1 to both sides. 9 plus 1, you can't take the square root. So I know it's not factorable. So 9 plus 1 is 10. This is factorable. It's -1 and -1. Take the square root of both sides. It's real, no i's, and then add 1. So if I would do the complete linear factorization, this is what it would look like. So it would be f at x equals x plus 4. That's where the -4 comes in. And then it would actually be x subtract 1 plus root 10 and x subtract 1 minus root 10. So you subtract each time. You could distribute, and one would be subtracting, one would be adding there. But that's what it would look like for the linear factorization. The zeros would be -4, 1 plus and minus root 10. So all this is real, but one's rational and 2 are irrational. 34. Can you identify the zeros, the multiplicity, and so on here? So this is already factored. So x cubed, x by itself, it's 0. The multiplicity is 3. That's the exponent attached to it. And that means it's going to cross the x-axis. Here we got positive 3 over 2. It has an even exponent. So that means it's going to touch the x-axis. And then the last one, that's -7. It has an odd exponent, so it's going to cross. That's it. Try number 35. is not factored yet. That's not fair. So I need to factor it. So I factor out an x cubed to begin with. So you're left with x cubed subtract 2x squared subtract 4x plus 8. That is factorable. Take the first two, factor out an x squared. The last two terms factor out a -4. So then all together, I can factor it. That's x minus 2. Now x squared subtract 4 is x minus 2, x plus 2. So it actually end up being x subtract 2 squared. So x squared subtract 4 is a difference of squares and ends up having 2x minus 2. So we already had an x minus 2. There's another one. So we square it, and we still have an x plus 2. So x cubed is 0, and the multiplicity is 3, and that means it's going to cross the x-axis. Here, it's positive 2 with an even exponent, so it's going to touch the x-axis. And then the last one, -2, you don't see it, but it has a multiplicity of 1. An odd exponent means it's going to cross. Great analysis skills. Do you have the ability to factor and to understand the zeros and multiplicity and what it would do if you graphed it? All right, next page, which is our last one. Number 36. So 0 and -1. So use the zeros to form a polynomial. So every 0 has a factor. So for 0, the factor is x. For -1, it's x plus 1, but it has an exponent of 2. This one's trickier. You got to multiply by 3 and subtract 4. So you kind of have to do the inverse. So times 3, subtract 4, and then you multiply it out. So the easiest thing to do to multiply this out, take the first and the last. So that's 3x squared minus 4x. And then multiply x plus 1 squared out. That's x squared plus 2x plus 1. Then FOIL one more time and combine like terms. So first times first, 3x to the fourth. First times middle, that's 6x cubed. First times last, that's 3x squared. Now take the next term, negative 4x, that's negative 4x cubed, negative 8x squared, and minus 4x. Last step is to combine like terms. So we have 3x to the fourth. 6 and negative 4 is 2x cubed. 3 and negative 8 is negative 5x squared. And then a negative 4x. Done. So this function has these zeros. We have the ability to write them as factors and then expand. 37. So plus and minus 5. So that's, these are the factors for that. And then same thing with 3 root 2, plus and minus. Now the good news about multiplying these are a difference of squares. So you'd end up with x squared minus 25. And we just need to know how to multiply 3 root 2 and 3 root 2. So 3 times 3 is 9, and root 2 times root 2 is 2. So that's 18. So it's x squared subtract 18. And now multiply it out. X squared times x squared is x to the fourth. Negative 25 and negative 18 is negative 43x squared. And that's a big positive number. 18 quarters. You probably know how much money that is. 16 quarters is $4. So it's $4.50. Is that right? $4.50? Done. All right. 38. If it's money, right? We can do it. So this one's missing one. So it's negative 1 plus 3i. They always come in conjugate pairs. So we have x plus 3. We have x subtract negative 1 subtract 3i. X subtract negative 1 plus 3i. There's a start. I'm going to keep going for fun. That's x plus 3. That's x plus 1 plus 3i. This is x plus 1 minus 3i. I'm going to multiply the two imaginary ones together. So let's do it. X times x is x squared. X times 1. X times negative 3i. They're going to eliminate. 1 times x. 1 times 1. 1 times negative 3i. And then 3i times x. 3i times 1. They're going to eliminate. And then this is the tricky one. 3i, negative 3i. I wonder if you remember that when you have 3 times negative 3, that's negative 9i squared. But I squared is negative 1. So in other words, it's negative 9 times negative 1. That means it's plus 9. Now, the good news is that the i's are going to eliminate. So really what I'm left with is x squared plus 2x plus 10. Yeah. And then if I multiply this out, x times x squared, x times 2x, x times 10, 3x squared, 6x, and 30. Combine like terms, and you finally have the function. Any work I make you do, I do it all. For all my classes. So x cubed, 2 plus 3 is 5x squared. 10 and 6 is 16x. And then 30. So if you would find all the zeros and work backwards, you would find that you probably have to do the complete the square. You would have to complete the square at this point. It's to be able to work backwards. So can you work forwards? Can you work backwards? Backwards, forwards, backwards, forward. Oh my. Here we go. Last part is inequalities. Can you solve these inequalities? So step one is to know it's 0 on the right side, and then we have to factor if we can. So I'm going to factor an x squared, that's 2x plus 5. Factor a negative 16. I was going to do 8. 16. That's x plus 5. So I have 2x plus 5. X squared subtract 16 is a difference of squares, so I'm not going to waste your time. That's x plus 4, x minus 4. And now we have our zeros. So negative 4 is a 0. Positive 4 is a 0. And this is negative 5 over 2. Negative 2.5. All right, so those are my intervals. I need to know where the positive intervals are. So first I'm going to plug in negative 8. Again, I'm just looking for the signs. So it's a negative times a negative times a negative. That's not the interval I want. Next, I'm going to plug in negative 3. So negative 3 is a negative times a positive times a negative. That's a positive answer. That is an interval I want. Next, I'm going to plug in 0. 0 is a positive times a positive times a negative. Not the interval I want. And then any number bigger than 4. So I plug in 6. And everything is going to be positive. So it gives you a positive answer. So my AND answer are the positive intervals. In all parentheses, because it's greater than 0. So negative 4 to negative 5 over 2, and then 4 to infinity. All right, number 40. Not a 0 on the right side. So let's bring everything to the left side. So I'm going to subtract 4x squared. I'm going to subtract 5. Not factorable. 1. Oh, I like that. So 1, if I go negative 4 and negative 37, that's negative 41 and positive 41. Because it adds up to 0, positive 1 works, and I'm going to use it. So that's a handy one to know. All right, that's done. Now what's left over is factorable. So x squared minus 3x minus 40. So if I put this all together, positive 1 is x minus 1. The two numbers here are negative 8 and positive 5. So negative 8 and positive 5. Now it's completely factored. The 0 on the other side. So I have positive 1. I have positive 8. Remember, this goes on forever to the right. And negative 5. So now I just need to test each interval. So like if I start with negative 8, that's negative, negative, negative. If I put in the next one, let's say 0, I like that one. Negative, negative, positive. So this is what I want. I want the negative answer, not positive. Plug in 2. Positive, negative, positive. So negative, negative, that's going to give you a negative answer. And then plug in a number bigger than 8. And everything's positive. All right. So where are the negative intervals? And we're going to use brackets because of the line underneath the arrow. So the answer is negative infinity to negative 5, bracket. And 1, bracket, to 8, bracket. So answers from negative infinity to negative 5 give you a negative answer, and from 1 to 8 give you a negative answer. And you solve the inequality. All right, last two questions, 41 and 42. So step 1 is to factor it. We have a 0 on the right side, so that's positive 4 and negative 3. So the zeros of the numerator are negative 4, that's an intercept, and positive 3, that's an intercept. And the denominator is asymptote. So at 1 is an asymptote. So those are my intervals. So plug in negative 6, a negative times a negative, divided by a negative. Altogether, that's a negative answer. Plug in 0, and you get a positive answer. Plug in 2, and everything but one thing is negative, so it's a negative answer. And then plug in 4, and everything is positive. I want greater than 0, so the intervals go from negative 4 to 1, and from 3 to infinity. Done. Oops. So negative 4 to 1 and 3 to infinity. Those are the intervals that give me a positive answer. Last one. How awesome. It's not equal to 0. Subtract. We need common denominators. Use the other denominator to make common denominators. Put this together. 7x subtract 6x. That's less than or equal to 0. So 7x subtract 6x is 1x. 14 take away 18 is negative 4. So that's what it looks like when you put it all together and combine like terms. So it's less than or equal to 0, so be careful of that. The numerator, positive 4, that can be a bracket. Negative 3 cannot be a bracket. Negative 2 cannot be a bracket. All right, so those are my intervals. So I'm going to first plug in negative 8. So that's a negative, a negative, a negative. That's a negative answer. Plug in negative 2.5. Negative 2.5 is a negative, a positive, and a negative. That's going to give you a positive answer. That I don't want that interval. Plug in 0. That's a negative and 2 positives. That's a negative answer. Plug in 8. Everything is positive. So look to know what you want. Where is it negative? And then write the answer down. So from negative infinity to negative 3, parentheses, it's negative. It's also negative from negative 2 all the way to 4. And be careful, 4 is a bracket. So from negative 2 to 4, 4 is a bracket because it's an intercept, an asymptote. You can only use parentheses. All right, that was a lot of work. And you did it with me, and I did the work too. Whatever. It's good for us. You know, the factoring, the working, the graphing, all of that, that's good work. And you did it. I'm so proud of you. So Mr. G Math over and out. Until next time.